All right, hey, what's up, guys? So today we're gonna be going over data structures or chapter 4. Um, as always, feel free to stop me if you have any questions. Um, but anyways, let's get into it. So, basically what data structure is it's gonna allow us to store like different types of data inside of something. It kind of does exactly what it says it does. The most obvious example of this would be like the regular array where like you just throw in like a bunch of integers or strings in it. But now we have different types of containers that will allow us to like do things either more conveniently or more efficiently. So the first example is the dynamic array, which is better represented as the vector in C++. And basically what it does is it's the same thing as an array, but the word dynamic basically references that it's resizable. So it doesn't have a fixed size, and if you always want to add something else to the end, you can. When you use a regular array in C++, let's say you like define it with size 4, if you have to add something to the end, you can't quite do that. But with a vector, you can define it empty and then just continuously push things back. So it's gonna be a lot more useful when you don't necessarily know, like, at initialization time, how many elements to expect in it. So, so right here, this is just syntax to iterate through all the elements. You can use v dot size to iterate through everything. This will return how many elements. This is the equivalent of like the size of a static array. An easier way to iterate is using this for each loop using the auto keyword, and you can do this with almost every single one of the containers in this section. I think the only exception should be the stack and the priority queue. Actually, I'm not too sure if you knew the priority queue. Well, we'll check it when we get there. So, back will return last element in the vector. Pop back removes the last element. Um, they don't go over it here, but one of the biggest parts about the vector is if you erase from a vector, the time complexity is actually O of n. So if you erase something in the very middle of the vector, it's going to be really efficient and it's going to be way too slow. So if you have a problem where you have like a ton of elements, like let's say 10 to the fifth, and you're constantly looking to remove elements and also like insert them, then it's just not going to work because removing stuff from the beginning of the or the beginning or the middle of the vector is going to take O of n time, so it's going to be really slow. The only thing that you can do really fast is remove stuff from the very end very quickly. So removing the last element in a vector is still going to take O of 1, and you can use a pop back for that. Insertion time, which is used by pushback. So if you use the pushback function, it inserts something into the back. That'll take O of 1 times, so that means that adding something to a vector is very fast. So as long as you're adding something to the end or moving something to the end, then you can do it in O of 1 time in a vector. If you're doing either in the middle or the beginning, then it's going to take a little more time. So basically, there's also the string, which they say you can think of as like a vector because it's just got a bunch of characters that you can append to the end of it at any time. There's some convenient functions in there like substring, which will just give you like a specific substring inside of it. The confusing part about substring is if you pass two parameters, it's not gonna denote like the beginning and end. So like this 3 and 4 isn't saying like output indices 3 to 4. It's actually saying start at index 3 and then get 4 characters. So you'll see that if this is the whole string and we want to output b dot substring 3 comma 4, it starts at index 3, which is this t, and then it gets 4 letters, which is the tiva part right here. Um, so next up, we have the set. So the set's really good at basically telling you if you have something or not. So you're gonna be able to retrieve and insert in really fast times inside of a set. So operations work in log n time. There's something called an unordered set, which is the same thing as a set, except it's not ordered. So if you were to put stuff into a set and then output it, naturally it's already going to be completely ordered. And if you do want it to be ordered, each operation is going to take log n, but if you choose to use the unordered set instead, it's going to take O of 1 time instead. So, like I said, one of the best uses for the set is saying if you have something or not, because you're going to be able to check if your container has an element you're looking for in log n time. You could binary search for something in a vector, but the problem is like if you need it to be sorted like in a vector, there's no way to like insert stuff and then have it sorted afterwards without like sorting at each step, which would take a while. So if we look at the example they give us, like they show us how to initialize a set, which is basically the same thing as a vector, except like you replace the vector part with set. So the way you're gonna initialize all these data structures is you're gonna put like the type of data structure you want, and then your data type inside these angle brackets, and then your variable name after. So inserts how we're gonna put stuff inside the set. So we're putting 3, 2, and 5 in, and then we can use s dot count to see if we have something or not. It's gonna return either 1 or 0. So 1 if we have it, 0 if we don't. And the thing about the set is it won't hold duplicates. So as they show here, all their elements are distinct. So this means that one of the most useful applications of the set is to like weed out duplicates. So like let's say you were given an array that potentially had duplicate items and you only wanted to end up with one of each, then you could push everything into a set to see how many unique items you have because it would get rid of the duplicates as you try to insert them into the set. So what they do here is they insert 5 3 separate times, and then they use s.count to see how many like occurrences of the 5 there are, and there's only one. So if you try to insert something into the set that's already in there, it's going to nothing's gonna happen. The original element's gonna stay in there, and then only one instance will exist in the container. And then up here, once again, just showing you how to iterate through a set using a for each loop. Um, so if you do want to hold multiple instances, you can use the multiset, which is quite literally the same thing, except now you can hold multiple instances. So once again, they'll insert 3 instances of 5, and then now if you use s.count on 5, you'll actually get 3. And internally, if you iterate through this multiset, you'll actually have 3 5s in there as well. So one thing to be careful of is now that you actually have multiple occurrences of the same element, when you use erase on a multiset, it's not going to erase like just one of them, it's gonna erase every single instance, which is something that I messed up quite a bit when I first used multiset. So if you want to iterate through a multiset and check if you have something and then only erase one of them, you have to erase the iterator instead. So you can do this by using s.find and then passing in what you want to look for. So find will get you like the iterator to like the index of this 5, and then it would erase like only that index. You could you don't necessarily have to use find. It's like the shortest one, but like you could always use like lower bound as well.
What are some examples where we can use the multi-set over just like a regular value that we increment when we have something?
Um, if I'm being honest, multisets aren't really used often. Uh, in fact, I can't even like think of like a problem where I like right now off the top of my head where you have to specifically use a multi-set. I've realistically only used it like a few times. Um, you would just kind of get to know like when you should use it, like depending on the problem. Like I said, you would literally only need this if you needed a container that would store a bunch of stuff. Like you would still need a set, but instead you need to store multiple occurrences. So what I can think of is like maybe like you just need to store a bunch of like possible items to pick from like array elements that might serve as like valid answers, and you're going to like retrieve the most optimal one quickly. So like instead of like searching for it in like a vector, you you use dot count to see if like it exists, and like it also happens that like you have multiple of the same answer in there. Or not answer, but like multiple of the same like usable like elements. Um but like I said, this might be wrong, but I haven't used multiset very often, and it's mainly because you don't actually need a multiset to solve problems. There's usually a workaround. For example, if you want, you could just use priority queue for a lot of the same things. Um, but uh, but yeah, if I'm being honest, I can't think of a specific problem for multiset. You're just gonna have to figure it out when the time comes. Moving on to maps. This is probably one of the most important ones in here. Basically, a map stores like a bunch of different pairs where if you put in the key, you'll get the actual value. So um So the way you initialize it is since it's a pair of stuff instead of like just one element, you still use map and then your angle brackets, and then instead you put the two like items you want in here, with the first one being the key and then the second one being the value. So what we can notice here, since our key is a string in this case, we can do like m of like monkey is equal to 4, m of banana is equal to 3, and then like a bunch of other stuff. So one thing that I think is a little easier to understand how like a map works is you can kind of think of it as like accessing an array, because like in an array we use this bracket notation, and then we use like a integer to like index our array, right? Well, instead of like getting like a and then like a 5 in brackets in a vector or array, you're able to use a string instead. Um, and that's gonna be one of the most convenient uses of the map is you can store stuff, but you can store how many occurrences you have of something, but you can also like connect strings to integers. So let's say like you have a problem where like I don't know, you have like a bunch of like people's names and you need to like link them up to like a specific ID, then this would be the easiest way to get those. If the value of a key is requested and the map does not contain it, it's gonna be created with a value of 0. So let's say this like key does not exist in the map, so we've never used it before. Um, if it doesn't exist in the map, then what happens is they're going to create it and set its value to 0. So um like let's say you created a map with all of these and you like iterated through it, you would have all of these, and then as soon as you like try to see what the value of this is, since you've never made it, it's gonna go ahead and create it for you and then set it to 0. So if we iterate through our map before we like call this, we're not gonna have it, and then if you iterate through the map afterwards, even though like like you're just checking the value and you've never set it or anything, it's gonna go ahead and create it anyways and set it to 0. This is actually pretty important because you usually want to only like access this if you know that the element exists in the map. And the reason for that is there's a lot of problems where you're going to use this bracket notation to check like how many occurrences of like a potential answer you might have. Like, there's a lot of problems where you might be searching for something that isn't guaranteed to be in the map. So if you're constantly using this notation to check if something exists, you're gonna continue to create like new pairs in the map, which will make it significantly slower. So what I'm trying to get at here is you should only use this if you know that it exists in the map. If it's not guaranteed that this key exists, then you should probably check first to see so you don't create a pair in the map. And once again, if you like continuously like check stuff that doesn't exist, the size of your map is gonna be huge and it's gonna slow down how much time it takes to get everything else. So the way you can check that something exists before using this notation is it's gonna be the same thing as the set. You're gonna use dot count. And they tell you right here. So the function count checks if a key exists in a map. Once again, auto key with for each loop to iterate through it for convenience instead of using iterators. Um, do they? Yeah, and they show you down here how to actually like use it without auto. But basically here they go over iterators, and as I was mentioning earlier, with the multi-map, deleting every instances, so you have to use an iterator. An iterator simply like points to like an index in a data structure, or like it points to like an element more specifically. So usually you're going to be using dot begin and dot end because like you want to go through the whole range. But but the way that we're gonna iterate through like a data structure is we can't do the like for int I equals 0, I less than the n like I plus plus method we do with vectors. You're going to have to declare an iterator to the beginning and then increment it and stop it when it reaches the end. And they'll show you how to do that later down. So with a lot of data structures, or like almost all of them actually, you have a begin and end function that will provide you the beginning and end iterators. So if you want to sort, you pass v dot begin and v dot end. If you want to reverse, same thing, and then random shuffle would be the same thing. Um, if you want to do it with an array, like a regular array instead of a vector, then you would just pass like the name of the array and then the name of the array plus the size, which would also get you to the address of like the last element. So if you want to know how to iterate through like these data structures without using the auto like and for each like syntax over here, then this is how you do it. You'd initialize an iterator and set it to the beginning. So set int iterator it equals s dot begin, and then you would do like while it is not equal to s dot end. So they use auto here to replace this, but you can kind of think of this as like set int iterator it equals s dot begin, it not equal to s dot end, it plus plus. Um, if you want to get one of the most important things is the the end of a container, so it's at back iterator, it doesn't necessarily point to the last element, it points to one before it. So if you wanted to output the last element in like a set, let's say, you don't output like s dot end, you have to decrement it first and then output it. And once again, it's because the last element in a container, or sorry, the iterator doesn't point to the last element, it points like one after it. And then over here we just have like some functions. So they show you how lower bound will return you an iterator to the smallest element in the set whose value is at least x. So basically, if you want to find like the index like of a element in a set, then you would use lower bound and it would return to you like an iterator to like that element that has at least value x. So just skipping through um yeah, this is like that same thing of like finding the element nearest to x. So if we look through the last few data structures in here, or actually no, there's quite a few more to go through. So a bit set is an array whose value is 0, 1. If I'm being honest, you don't tend to use these too well or too often. Because the main like pro is that it uses way less memory because you only have zeros and ones at each index. You don't have like an entire integer. So So, I think I think it uses an eighth of the memory that an integer array would use if n bits are stored in int array 32n. Okay, so 1/32 in this case. Oh yeah, 1 bit instead of 32, obviously. Yeah. It uses 1/32 of the memory. And basically what you can do is you initialize it a little differently than some of the other data structures. So bit set, and then inside of the angle brackets is the size. And then what they're showing you here is that you can actually like initialize the bit set by passing in a string in its constructor. In order to get the like value at each index, you do the same thing with a vector. You just use this like bracket notation. And then the pro to using bit sets is like they use less memory, and if we want to manipulate them, we can use bitwise operators on them as well. So bitwise AND, bitwise OR, and then XOR. Um, count, if you want, uses the number of ones in the bit set. Or it'll tell you how many like set bits there are. Bit sets like I said, bit sets aren't too useful. It's mainly that they use less space. There are times where they are faster and like necessary to solve a problem, but that's extremely rare. In fact, I'll leave a YouTube video in the Discord for that, but as like a really good video to as to when to use bit sets. But generally they're not too important. Um so moving on, deck, it's pretty much the same as a vector, except you now have push back and pop back. So a deck has constant time operations on both ends, as they say down here. So, like I said earlier, if you want to insert into the beginning of a vector, it's going to take a while, but if you like push something into the back of a vector or remove from the back, it's O of 1 time. Well, a deck is O of 1 on both ends. So if you have like a simulation problem where like I don't know, they have a game being played between like two people and they can like take elements on like each end and who ends up with the last element or something, then in that case it might be easier to use a deck because then you can like literally simulate the problem by like just removing from the back or the beginning. Um Once again, these aren't used as often as some of the other ones, but they can be convenient once again when like you do want that constant time operation for the beginning or end. Um so a
Is
stack,
there? Oh,
oh
sorry.
good.
Is there a certain reason we would use a like vector instead of a deck for different problems? Like, does a deck take more memory, or is it? You said it like it's faster on the, when you take it takes O1 operations for the front and the back, but like, why would we use the vector for certain situations compared to the deck?
The deck is like it's like it's a little quirky, I guess. It's got like a lot, I mean, as they say here, it's got like a lot more stuff in it, and it's just like a little slower. I don't know how much slower if I'm being honest, but it's more so that like the pros of like a deck are like a lot like you don't get that many advantages out of it, and the performance like decrease just makes you like not want to use it even more because like I said, I would only really use this if you have that case of like you want constant time operations to the front and the back, because almost never are you actually going to need them. So yeah, the main reason you use a vector instead is for performance issues. And I'm sure there's other functions in like a vector that you don't have in a deck, but I can't I mean, there's a lot of like major ones that like a deck doesn't have. I mainly just use like vectors because it's like the more popular one as well. So you're gonna be a little more familiar with it. Um, as well as like it's just a little faster. So if you don't get that much more usage out of a deck and the vector's faster and it's what you're comfortable with, then just use the vector. I think that's what most people use. Um, if we keep going, stack basically. Um, it's it basically you can think of it as like a stack of plates. So if you put a new plate on the stack, then it's gonna be the first one you take out as well. And that's kind of like the logic behind a stack. So the last element that you insert has to be the first thing that comes out as well. So here if we push in 3 and then 2 and then 5, they have to come out like in this reverse order. So you would have to remove 5 first, and then 2 and then 3. And what this basically kind of means is you only have access to the element that's at the top. So like in the case of us having these three elements pushed in this order, we would only have access to this 5 at the very top. Stacks don't have random access, nor do they have iterators, which means like if you want to like see the contents of a stack, you have to make a temp stack and then just like output the top and then pop and continuously do that until it's empty. Um, Stacks are pretty useful with a lot of algorithms just because like a lot of the times you want to process the immediate thing that you just added. So the most popular example would be a depth first search, which is a like graph traversing algorithm in which as soon as you like find a new place to visit, you visit all the places you can go from that place. And then when you choose a new place, like a new destination, you immediately check all of the places it can go from there. So you basically continuously like go as far out towards like each place's like other routes as you can. Um Depth first search is a little more advanced. I think it's a little more chapters down. But stack is basically used whenever you want to like process something that you just added immediately. Um the queue is basically the opposite. Um, Once again, easier to imagine when you relate it to something in the real world. So you can think of it as like an actual queue or like a line at a grocery store. So whoever goes first in line is the first person to check out. So first thing you push in is going to be the first thing that comes out. So I think they give the same numbers here, so 3, 2, and 5. So if you push 3 first and then 2 and then 5, since the 3 was first, um, it's what you have access to, and then if you remove it using q.pop, the next one is 2. So once again, you only have access to the first, here it says first and last element, but usually like we only want the first one anyways. Um, you only have access to the first element essentially, and like the whatever you insert first is going to also come out first. So this is kind of like I guess the opposite of a stack and a better like a tougher like analogy as to like what it's used for is instead of a depth first search in this case, there's something called a breadth first search where instead of like immediately trying to process the first thing we added, so in the stack like you would push something and it would be the only thing you'd have access to. Well, in the queue it's like the opposite way around. So the when you push something in, it's going to be the last thing you get to. So this is the opposite case where we want to handle like all of the things that we pushed in first before we deal with any of the stuff we push in later. Queues are how we do breadth first search, which is a graph traversal method that is like kind of like the opposite of depth first search, where instead of like trying to visit like things immediately after we reach a new place, we're gonna kind of go out like in order. So we're going to go to all the destinations of like the first thing like we're at, and then we're gonna go to all the destinations of like the next available unvisited node. Once again, it's graph algorithms, so if you don't understand graph algorithms, it's okay. If you do understand them, it helps a lot with understanding these. Um, Priority queue, this is single-handedly one of the most important ones, and the reason is because it's really fast and it does stuff that a lot of other like containers just aren't able to do. So what a priority queue does is it binary searches before it inserts something. So what this means is that inserting is log n time, and so is removal. So uh what happens with a priority queue is you can kind of think of it as like it's still got queue in the name, so you only have access to the first element, except now like it's got priority in it, right? So what this basically means is instead of accessing like the first element that was pushed in, you're going to access like the element with the most priority. So generally speaking, this is going to be the either the element that is the biggest, so the biggest number, or you can sort it the other way where it's the smallest element. So what happens is if you push like let's say these four numbers, you're only going to have access to the front, but what's going to be at the front is the biggest number. So it's auto sorted like automatically as it's inserting its elements. So if you initialize it like this, then by default it's going to be sorted in descending order where the biggest numbers come first. So you'll notice if we use q.top here, notice it's dot top to access the first element instead of dot front as it is in Q. You might be mixing that up when you're using these. Um, if you get the like element at the top with these four elements, you're gonna receive the biggest element, which is 7. If we remove the 7, the next biggest element is the 5. And then what they're doing here is they're inserting the 6, which would be the next biggest element, or more so like the new biggest element, because now you only have a 3 and a 2 and then a 6. So what's gonna be at the front is gonna be that 6 that you just added. So if you want to do it the other way around, so instead of getting access to the biggest element, you want the smallest one, you use this notation instead. And what you do is this first one's going to be the data type that's going to be stored inside of it, so kind of like the same as this up here. This second one is going to be like a container for it to like sort. So like I guess a way to think about this is like you just pass vector and then the data type in your priority queue inside of that vector. I think that they only need this to be able to like sort it like in the order you want. So like by default, like they already have it. So like if you want it in like decreasing order, so greatest to least, it's already like implied. But in any other case where you want to change it, you have to provide this container to them. And then passing the greater int is like quite literally passing like the greater than sign, where you're telling it like the order in which it sorts to. Um it's not too I wouldn't say it's like too specific to know like the inner mechanisms as to how this works, but it's also not too hard to remember it as like the data type that you want, the container, and then pass in like greater int to like to tell it like which way you want it to sort. These are this is when it starts to get a little weird. So these are called policy-based data structures. So basically they're like super advanced data structures that aren't in the STL, but they're instead in the G++ compiler. So in order to include them, you're going to have to like use this header instead of um like include map or bit slash std++.h. So after typing in like this, you can they like to use a type def to make initializing and index set a little easier. But using this will let you import some of the like crazier data structures that they have in the C++ that aren't in the STL. So this is something called an index set, which is literally the same as the STL set, except now you have the index of every single element. Um, Very rarely do you actually need the index of all of the elements in your set, but in the case you do, one of the this will be usually one of the only ways to solve it. Um, so what I'm trying to get at is they're very rarely used, but when you do have to use them, they're extremely useful. So the way you would be able to get the index is use the find by order function, and this will just return to you like the index. Oh wait, no, it returns you an iterator and then whoops, other way around. So find by order will return you an iterator to the element, and then it's order of key, which will give you like the position or index that it occupies in that set. So once again, don't worry too much about these because you won't have to use them too often. I've only have to use them in one problem where what they were asking is you have a bunch of elements in a set and you want to know what index um like a certain element is, and then you have to remove it after. So because you have to remove it and all of the indices change, um, if you were to do it in a vector, right, you would still have like all the regular indexes, but removing from a vector would be like too slow. And if you wanted to like remove from a regular set, like the one in the STL, then you would also not have the indices. So it's really only useful when you have to like remove really fast, but you also need the indices. Um, Once again, pretty niche data structure. It doesn't get a lot of usage, but still useful nonetheless. Let's see. And then last one here, last thing in the chapter, they just give you some examples of like things you can do instead of sorting. So because so because like the set's like auto sorting, you can sometimes use it to like substitute actual sorting like in a vector. And here they're gonna give us a problem where like they're just gonna compare all of like the different ways that you can tackle a problem with sorting. So let's say you have two lists A and B, and you want to see the number of elements that belong to both lists. So they give us three possible solutions. So we can use a set and have all of the elements that are in the array A, and then you iterate through the elements of B, and then if you find an element that's in A, then you know if basically if you use like s dot count to retrieve like the current element that you're traversing in B and you have it in your set, that means that there's a match because the set stores every element that's in A. So if you like check in the set and you have like an element in B in that set, then it exists in both. So so what they're saying is that this first solution is you can use a set to check if the elements in B exist in A, and the time complexity of this will be n log n. Um, since we don't really need the set to be sorted, they say like we can try using an unordered set as well because we're only checking if something exists. There's no reason to make it sorted. So instead of the n log n time complexity, we get O of n because in order to maintain a sorted like set, it takes log n operations to insert it instead of constant time. So the total time complexity of like using a set or iterating through it will be n log n. Um, so and then the last solution is they just say like sort both arrays and then like iterate through them like at the same time and like increment your counter whenever like the two values match up. So you'll notice that since sorting is an n log n algorithm, time complexity of this is n log n. So the algorithm 2, the O of n, or the unordered set solution actually has the best time complexity because um O of n is like generally faster than n log n, but what they're trying to show you in this chart is that the sorting algorithm is actually the fastest. So the algorithm 3, just sorting them takes like less than a second. The unordered set takes 2.3 seconds and the set takes 10 seconds. So what you can kind of get from this is that a lot of these data structures have a lot of like stuff built into them, and it's going to take a lot of time to do a lot of these operations. So even though the time complexity can technically be better on the unordered set solution, the constant time factor is like really high because there's a lot of stuff it has to do internally when you're like inserting and working with an unordered set. So as they say here, algorithm 3 is the fastest, the one that uses sorting, and then it's explained because sorting is a pretty simple thing to do, and you just do it once, and then algorithm 1 and 2 as well, like they're more complex data structures, which will take a lot more work to maintain. So I believe that's everything. Just a bunch of spam of data structures. Um, are we good? Any questions?
It was very thorough. Thank you very much.
Thank you. Okay. Um, Cody problems are up as always. Solutions will be done after. Um, maybe I'll record those as well. But all 7 of these problems are solvable with data structures. So don't worry too much about the ones I said were not as common. So the bit set, the the policy-based data structures, but all of the useful data structures will be like utilized to solve these problems. So yeah, in any case, I guess that's it. So get to your problems and we'll go over solutions in a bit.